In this question, we've been asked to draw the free body diagram of the arm, as well as to calculate the magnitudes of the muscle tension and joint forces at the elbow joint. So I'm going to go through the steps required to solve a static equilibrium problem. So the first, like when we're drawing our free body diagram, is to identify the system of interest. So the question's asking for elbow forces as well as the biceps force. So that means we need to disarticulate the forearm at the elbow. So like we did with example 1. Okay. Step number 2 is to draw the free body diagram. So we could break that up into the subcomponents to incorporate the strategies to draw free body diagrams, but for the sake of brevity, I refer you back to example 1. So I'll just draw the free body diagram here. So we have the forearm, we have our non-contact force being the weight of the arm, and the question tells us that the weight of the arm is 20 newtons, so about 2 kilograms. So we can leave it like that for the moment. The next force we need to include, or forces we need to include, are those that result as consequence to our disarticulation. So we need to represent where the humerus would be touching the ulna, and we also need to represent where the biceps would be pulling. So we'll put the biceps force in here, and I'll call that the force of the muscle. And then remember, with the joint forces, we're just guessing their directions, and we'll see whether our guess is right later on. So we have joint in the Y, joint in the X. And then the last thing we need to include in terms of forces is the remaining contact force, and in this case it would be the weight of the ball. And the questions told us that the weight of the ball is 80 newtons, so around about 8 kilos. To complete our free body diagram, we need to include dimensions, because we need dimensions to make moment arms. So let's just interpret what the question is saying. It tells us that from the joint center to the insertion of the muscle, it's 40 millimeters. Okay. From the center of mass to the joint center, it's 150. And from the joint center to the ball, we have 350 millimeters. Don't forget your freebie marks, including your axes. So we're going to use Y as up and X to the right. So now we have a complete free body diagram. We can follow the rest of the steps. So I'm going to shift that up and work through these steps, so that's all visible still. Okay, next, the question or the strategy says that we resolve each vector into components. And at this stage of the analysis, I would just do this graphically. I would wait until steps 7 really to actually resolve the vectors mathematically. So just do it graphically. Now in this question we have the luxury that all our vectors are either in the Y, so they're either pointing up or down, or they're in the X, so they're pointing left or right. So we don't have to do anything. That step is done. Moving on, next step in our strategy to solve problems of equilibrium is to identify the point about which to take the moment. Okay, so the point that you choose, in reality you could choose any point. What we try to do is we try to minimize the number of unknowns in the system by choosing a point that will make some forces centric. So in anatomical systems, we choose the joint center as our axis of rotation, or the point about which we take the moments. And by choosing the joint center, you'll see that Jx and Jy become centric forces, so they don't contribute to the moment equation. And so that makes our life a little bit easier, and we can solve for Fm when we apply sum of the moments equals 0. Next is to identify eccentric forces. So I've sort of given you the answer here, but that's okay. So remember, eccentric forces, their line of action will never pass through the axis of rotation or the point about which you're taking your moments. So Fm is an eccentric force, as is the weight of the arm, as well as the weight of the ball, because no matter how far we extend their lines of action, it's never going to fall through or pass through the orange dot that I've drawn. Okay. Next, and I'm running out of colour, so I might start down in purple again. Let's get the weighting correct. Is to calculate moment arms. Again, like step 3, I would do this just graphically at this point, and I would wait until step 7 to quantify the moment arms. So rather than calculate moment arms, it really should be draw. Now remember, your moment arms are the perpendicular distance from the line of action of the force through the axis of rotation. So in this case, we don't need to do anything because our forces are vertical and our distances are horizontal, and so they're already at right angles to each other. Take that step 6 a little bit further, and while you're looking at moment arms, I would also look at the direction in which each force creates the moment. All right. So if we work through Fm, now remember, there's lots of ways you can do this. What I would do is put my left finger on the orange dot, and I would keep it stationary. Then I would put my right index finger on Fm, and I would pull in the direction of Fm and see which way my page turns. And in this case, my page will turn anti-clockwise. So anti-clockwise for this. And remember, anti-clockwise is positive by our convention. Okay. Following this process through for the others, the 20 Newton force is pulling the arm into extension, so it's clockwise. Remember, clockwise is negative. And the same logic can be applied for the 80 newtons. So everything's set, and we can now apply our equations of equilibrium. So let's do that. Okay. What I'm going to do actually is just move this down so that we can keep the equations all on one page. So please just bear with me while I do this, and we can go from there. Okay, got there eventually. So we're now at step 7, where we apply equations of equilibrium. Okay, now I start with the moment equation because I know that will give me the muscle force, and then I move on to the force equations to get the joint forces. So the way we write this is I like putting the equation that I'm focusing on into square brackets. Then I show you the direction that I'm considering positive, and then I say sum of my moments. Then I use the subscript to tell me where I'm taking my moments about. So you could put an orange dot, or I like to just use elbow joint center, just so your reader knows where you're taking your moments about. So they must equal 0. So we've got 3 moments. We've got the moment due to the muscle, we've got the moment due to the weight of the arm, or the 20 newtons, and we've got the moment due to the 80 newtons. Okay. Subbing it in, remember that moment is force times perpendicular distance. We've got force. Now that one's pulling anti-clockwise, so that's a positive, times distance. So we've got 40 millimeters. Now remember, we've got to convert that to meters. So we divide 1,000 to convert millimeters to meters. Plus, now we've got minus, because it's pulling clockwise, 20 times 150 over 1,000. Plus, minus 80 times 350. And that must all sum to 0 because we're holding this posture. Alright, so we can rearrange that and we can solve for Fm. So let me just rearrange this. So we've got Fm times 0.04 must equal 20 times 0.15 plus 80 times 0.35. If we divide both sides by 0.04, we can work out the force required by the biceps to hold the arm in this position, and that should come out to be 775 newtons. Once we have the muscle force, we're in a position to calculate the joint forces, and we do that using sum of the forces equals 0. So I like to start with x. There's no particular reason, so sum of the forces in the x direction must equal 0. So what we do is we look back through our free body diagram and we see where if there are any forces that lie in the horizontal. So in our case, we just have one. And so we end up with Jx equals 0. So our original guess of Jx actually existing was incorrect. So we now know that the joint force will be purely in the y. So let's calculate that magnitude. So we repeat the process. Fy must equal 0. And now we're looking at all the forces pointing up or down. So we have, by our designation, Jy pointing up, Fm also pointing up. Remember, muscles generate tension, so it has to pull. And then we have the weight of our arm pulling downwards towards the center of the earth, and the weight of the ball doing the same. So if I substitute in what we found from our moment equation, we have 775 newtons in our muscle force, and then I just evaluate out this. We can rearrange that such that the joint force has a negative sign and a magnitude of 675 newtons. So that simply means that we've designated Jy up, and in actual fact it's pointing downwards. So we don't need to do anything, we can leave it at that. Now, as a courtesy to your reader, it's nice to summarize the joint force into one. Remember, sometimes we don't care about components, we want to know what's happening overall. And so we do that just by trig sometimes, but other times if we've just got force in one direction, we can simply say that we've got 675 newtons at 270 degrees. And that will be my answer.